So let's start off at the website. And we are in this section here. Now I've put up a lab, but you can start the lab this week, although I'm sure you're going to be spending more of your time on the assignment. But if I just go into the lab for one moment, um, depending on how far I get today, um, you certainly won't be able to complete this lab. I won't get uh, nearly enough stuff covered today. Really, this lab is meant to span perhaps over the next 3 weeks or so. And also, even though I don't like mentioning it now at this stage, but this lab is also the basis for the second assignment, the second and last assignment. But for those of you that are keen, I would say if you want to start working on this lab this week and or next week, because having looked at the calendar now, I have a lecture today. Obviously, I don't have one next week because Monday is a public holiday. Don't know if the Nanjing students are aware of that, so there aren't any lectures next week. And the week after that is the Easter break. So really, after today's lecture, I won't see you for about 3 or 4 weeks. I'm sure you're delighted about that. But so certainly in that period, in that 3 or 4 week period, you can certainly start on this lab. But either way, you won't be able to get any further than probably this section here. Let me remind myself. Yeah, you will be able to do that section. I don't know if I'll get into SNS today or not, so you may not be able to make a whole lot of progress, but I'm sure you've got lots of other stuff to do anyway in that in the next 2 to 3 weeks. So in terms of today's lecture, I want to continue on looking at these slides here. I've added some more slides to the deck. So that's where I'll pick up the story. And you remember the last day I started talking about AWS messaging or integration, which will facilitate this event-driven architecture that I was talking about, albeit 2 weeks ago now at this stage. And the whole reason we have messaging available to us on the AWS platform, well, sorry, just before that, the two main services that we're going to look at to achieve this messaging objective is SWS and SNS in the case of Amazon anyway. Two very quite old services. Certainly SQS. You might remember I said that SQS was Amazon's very first cloud service. So it certainly predates the whole serverless era. And originally the idea was that SQS would be used by two monolithic applications. If you had two monolithic applications that wanted to communicate with one another, one way they could do it is synchronously over HTTP, but there was issues then with that in the sense that you now have tight coupling between those two applications. So if one of the applications wanted to evolve itself in terms of its functionality and its interface, then that had an impact on the other application and all of the other issues that are related to tight coupling. So alternatively, your two applications, rather than communicating synchronously, they could communicate asynchronously. And that's what the SQS service was aimed at initially by AWS. So you had two monolithic applications possibly running on EC2, but not necessarily. Those two applications were remote from one another. And so rather than communicating directly, they communicated via this messaging kind of middleware, I suppose you could call it. SNS serves a similar purpose, but it has a slightly different um, kind of the way it actually operates is quite different, and we'll see that when we come to talk about it. So again, the idea is to avoid synchronous communication between your compute components, whether your compute components are large things like monolithic applications running on, let's say, EC2, or two lambdas that need to communicate with one another. And it's in the context of lambdas that we will be exploring SQS, but the principles are the same no matter what the size of your compute components are. You have essentially two actors in this scenario. You've got a producer and a consumer. Producer writes messages to the queue. The consumer reads messages from the queue. When the producer writes a message to the queue, bear in mind now, that does not trigger the consumer to read that message. If that were the case, then we're back with synchronous communication. The way it works is the producer writes messages to the queue, and at some stage, the consumer will poll the queue to check, are there any messages there that I should read and process? And that polling is, the frequency of it is completely configurable. It's completely unique to the consumer. It's kind of private to the consumer, if you like. The producer isn't concerned with it or doesn't necessarily know anything about how frequently the consumers are checking or polling the queue for messages. Hence, we've got our two components are decoupled from one another. Just before I move away from it, you can have multiple consumers all polling the same queue. This was the original idea now. And when a producer, you could have multiple producers as well, but when messages are in the queue, maybe this consumer here polls the queue first, and it gets the messages and processes them and then deletes them, which obviously means that these consumers here never get to see those messages. And that's intentional. So that's part of the SQS design. So if you like, if you have multiple consumers, then only one of them is needed. Only one of them will be able to process any particular message. If you want all of the consumers to process all of the messages, then SQS isn't of any use to you. That's actually where SNS comes in, which is the next service that we'll look at after this. However, we're not really interested in this multiple consumers model at all. We're kind of more interested in one consumer. There could be multiple producers, but certainly one consumer, and where our consumer is a lambda function, because that's what we know about. We know a lot about lambdas. Okay, that's just some general stuff which I won't go back over. The consumer, sorry, when the producer puts a message onto the queue or writes a message to the queue, that message can actually persist there for quite a period. It does have a time to live attribute associated with it, though. It doesn't live there forever. As in, if no consumer ever read it, the message isn't going to persist there forever. There is a TTL, or time to live property. Sorry, there's a TTL property associated with a message, which defaults to 4 days, but you can configure it to be less than that or more probably, but typically would be less than that. And so if no consumer processes a message within its TTL, then SQS will automatically delete that message from the queue. Ordinarily, though, the producer writes messages to the queue, the consumer consumes them at whatever pace they want to, but the consumer is also responsible for explicitly deleting the message from the queue. If the consumer doesn't do that, then it's not really behaving the way it should be. That's okay. I'll skip over the security. We had a one-on-one example, which I talked about the last day. I'm going to move on from that. From the CDK point of view, the only thing that's new, well, okay, this is how we declare a queue. It's pretty straightforward. In our case, our consumer is a Lambda, but there's nothing unusual about the way we declare the Lambda in our CDK code. This is how we connect up the Lambda consumer with the queue. We are making the queue the event source for our Lambda. Remember when we started talking about Lambdas, we said Lambdas Lambdas are triggered by the occurrence of some event in its environment. In this case, the event is related to uh, the uh, the existence of messages in a queue. I'm being careful. I'm saying I don't want to say that the Lambda is triggered by the occurrence of a message in the queue, because that's kind of suggesting it's synchronous again. Um, it's just only a small point. So the queue is the SQS queue is the source of the events for triggering the execution of our Lambda function. And the Lambda, this is just an excerpt from our Lambda. The Lambda always receives a batch of messages, even if there's only one message in the queue. It's still the Lambda consumer has to treat it as a batch, because that's how the this event object here, when we look inside the event object, we will see that the messages are always represented as an array, even if there's only one message in the array. And that's why we've got our for loop here iterating over essentially the body of the event, although it's the records within the event. The screenshot is a proof of that here. This is the console log of the event that my consumer Lambda receives. And here's the proof that, look, this is actually an array here of messages. The messages themselves are kind of buried inside. So this is one, this is one, some of it is being left out now. Let me see. Does it go all the way down to that's probably the majority of what's contained in a message, but really it's only this part here is the actual body of the message. So there's a lot of metadata, which may be useful in some cases, but we tend to ignore it. If the message is a JSON structure, then the consumer has to parse that. Just have to be aware of that. And that's proof of it there. I'm going to skip over that one, although I don't think I explained this slide properly to you the last day, so I will come back to it. In terms of scaling on the consumer side, the Lambda service, that's the other point that I'm making a lot of points that I made the last I know, but they're kind of important. The Lambda function itself, that does not communicate directly with the queue or with SQS. It's the Lambda service that takes care of checking to see, polling the queue to see if there are messages in there. And really what the Lambda service, even though this image isn't showing it, the Lambda service asks the SQS service. So it should really have SQS here. It asks the SQS service to check if there are any messages in this queue. And if there are, SQS will find them and return them back to the Lambda service. So the Lambda service now has a batch of messages, and it will actually it may actually create a number of instances of your Lambda consumer. Now, the documentation says that it creates 5 when I kind of read up on it. By default, we will always create 5 instances, concurrent instances of your Lambda consumer. That doesn't really follow through though when I sort of played around with it, but it certainly creates a number of instances, concurrent instances of your Lambda. So it kind of has a little bit of scalability from the very beginning. If the volume of messages that are being, so the Lambda will keep on polling the SQS service. However, periodically we can control how frequently it polls it. But let's say every time it does poll it, it does get a batch of messages every single time. And the amount of processing that the Lambda function needs to do is such that a new batch of messages may arrive before these small subset of concurrent Lambdas have finished processing the message. And if that is the case, then the Lambda service will just keep on scaling up the number of concurrent instances of the Lambda function that it needs to handle the throughput of messages that it is receiving from the SQS service. So the overall point is that the Lambda service will automatically, all right, just give me a second. The Lambda service will keep on scaling up the number of concurrent instances of your consumer as is required based on the throughput of messages that it's receiving from the queue. You can control that though. Maybe you only want a maximum of 4 concurrent instances to be instantiated. So you can set an upper limit on it. If you don't, then it'll keep on scaling up. And I'm saying down here, this gives you an idea down here as to how much it will scale up. It'll keep on scaling up. It'll keep on adding 60 consumers. All right. 60 consumers, concurrent consumers per minute, up to a maximum of 1,000. So, the 1,000 you might remember is the maximum number of lambdas, concurrent lambdas that any AWS account can have running at any particular point in time. So the overall point anyway is that the Lambda service takes care of scaling up your consuming Lambda for you, subject to your control though. Now, this is just another example that I started looking through it the last day, but this is where I'm going to pick up the story. So in this example, I've got a Lambda here, which is actually going to be my producer. So it's talking to the SQS service and asking it to write messages to the queue. This Lambda over here is my consumer. So if we look at that, so I've already deployed this stack. And if I just start looking at the code now, so we've got 2 lambdas. On the left is my producer, on the right is my consumer. And let's just look at the CDK code first. Now there is some additional code in this file which I've commented out because I'm going to uncomment it to illustrate another aspect of SQS. So we can ignore this up here. Here's the queue, the context here, Maria, is that the producer is writing orders to the queue and the consumer is consuming them. So where an order is something as simple as, okay, that's just the structure of an order. Nothing too fancy there. Let's go back and look at the CDK code. So here's the declaration of my queue. Now, there's a lot of stuff in here that I've commented out, so we're not interested in that. It's just an ordinary SQS queue. Here's the Lambda that's going to be my consumer. Here's the Lambda that is the producer. Skip over all of that. Here is where we are indicating that my consumer Lambda is triggered by the existence of messages in my queue. So I'm connecting up an event source for my consumer Lambda. And here, because the Lambda, the producing Lambda, the Lambda on the left on my diagram, because that is explicitly writing to the queue, then it needs permission to do that. So this is very like with DynamoDB. So I'm granting this particular Lambda the right to write messages to the queue. Note that the consuming Lambda, it never interacts directly with the queue, so it doesn't need any permissions. The mistake a lot of people make is that they give the consuming Lambda read permissions on the queue, but it doesn't need that and shouldn't get it. The Lambda service, all right, does need read permissions, but that's taken care of by AWS themselves. The messages that my consumer receives, it receives them in the form of the event object that's passed into my Lambda function. Okay, and I'm just outputting the name of the producing Lambda because I'm going to trigger that Lambda from the CLI. Now, if I look at the producing Lambda, which is this one. Let's see. Yeah. So again, this is just arbitrarily how I decided to set it up. So what I've got here is just an array of orders for myself. Okay. I've commented out this one because one of them is actually a bad order, but we're not interested in invalid messages at this stage for now anyway. So it's just an array of all good orders, looks like. And I've given each order, I've given them the customer name of user 1, user 2, user 3, etc., all the way up to, how many did I put in there? User 6. Thought I made it 7 actually, but it's okay. Let's leave it at 6. Let's leave it at 6 for now. So I've got 6 orders there in my array. Don't worry about this extra typing that's going on up here. This is just an array of 6 orders. And here's how I write to the queue. How do I write to it? It's quite similar to the way we interact with DynamoDB. We create command objects, except in this case, it's SQS command objects, and there are two. I think probably the only command object we will look at is to send a batch of messages. There's also send a message. The only reason I'm using send a batch of messages is because my orders are inside an array. And so I'm going to write the entire array of orders as a batch of messages to my queue. I could have alternatively just written a for loop and inside the for loop, iterate over the array of orders and send a message for each order in the array. It's either or, it doesn't make any difference. So I'm creating here, it looks like I'm creating an object of type send message batch. Send message back request. Now, when you're writing a message, the message in my case is just the order, which is kind of this line here. But the producer, is responsible for generating a unique identifier for each message, and that's what's happening in this line here. V4 is just a third-party library that I've imported here. You can use it for anything, for lots of different scenarios, but one thing it's useful for is for generating unique identifiers. And an identifier is just a big long string. It's not a hash value now or anything like that. It's just a string that is unique. So that's why, let's see, sorry. So what I'm creating here essentially is I'm creating a proper SQS message now, which has a body and it has a unique ID. So this thing now is going to be, this variable here is going to be an array of objects of this type. And then I create a command object, this one here, and I specify, and you can tell from the command object name that it's related to sending batch of messages to SQS. I'm just referring to the SQS queue, which I've passed in as an environment variable from the CDK stack. And I'm passing in my array of messages. And then finally, I'm just sending the messages to client. What's client? Client is my SQS SDK, which I have declared here. So similar to your DynamoDB SDK client, except here we're using the SQS SDK client. Okay, so I communicate with the SQS service. That's why I'm sticking an await in front of it, because the SQS service is remote from this Lambda function. By the way, if you leave out the await there, you won't get an error as such, but it's just one thing to be aware of. You know, it doesn't throw an exception. It's just kind of silent, and it can be difficult to debug why isn't it working, and you know you're just missing the await call, because at least when you do include the await call, now my Lambda function is waiting for a response back from the SQS service. If you leave out the await keyword, then my Lambda function sends the command to the SQS service, but it does not wait for the response. It just continues on executing. Obviously, we do need to wait for it. And let's see. Okay, we're just returning an ordinary 200. This now is going to be returned, if you like, back to the AWS CLI, because this Lambda is going to be, this is my producer Lambda. It's going to be triggered in my case from the AWS CLI. That's the producer. The consumer is here, here, and very little. I'm just, again, iterating over the batch of messages that are received from SQS. There's no real link between the batch of messages that this is my consumer that I'm looking at. There's no direct link between the batch size that my consumer receives and the batch of messages that I wrote with my producer. Okay, they are completely independent. Now, in my case, both batches will be the same, but that's just coincidental. So either way, anyway, this is my consuming Lambda, and I've already explained that it receives a batch of messages, which is why it's got this for loop. And I'm just iterating over, and I'm just console logging Looks like I'm console logging. Well, it looks like I'm using the AJV library, which you're familiar with, and I'm using it to validate that each message is a valid order. And I'm throwing exception. Where do I throw it? I throw an exception if it isn't. For now, we're ignoring those exceptions, but because when I was talking about producer there, all of my orders happen to be valid ones. So in a way, we're not really interested in this if statement for now anyway. And I'm just console logging I'm console logging the order. This console log now will be useful to us actually. We will be able to see in CloudWatch logs. We'll be able to see a number of things, which I think I'll just talk about maybe when we run this. So that's all of the code. We're not interested in this Lambda here for now. So let's trigger all of this. And as I said, I've already deployed it. And my CDK, it outputs the full name of the producer Lambda. So if I copy that, and here's where I put it in. But just before I run it, if I check in CloudWatch, I don't have any log groups at the moment. Yep. And let me just go back to the CDK for a moment. Just this line here, right? So this is where I am connecting up my consumer with the queue. Yeah. And the effect of this configuration setting here is to say this is essentially controlling the polling rate. So I want my Lambda service to poll the queue every 5 seconds. Yeah. So that means that when I trigger the producing Lambda, and then I go look on CloudWatch logs to see what log groups that I have, I probably won't see the log group associated with the consumer because the consumer waits for 5 seconds before it runs for the first time. Let's just see whether we can actually get that or not. And this is very much in the hands of the network now as to whether it refreshes quickly enough. But let's just trigger my producer anyway. Okay, and if I do a refresh here, and true enough, I do have the log stream for the producer. This is the generate orders one. I don't have the one for the consumer yet, but let's say 5 seconds has elapsed at this stage. If I do another refresh, and I have both of them at this stage. So we're really only interested in the consumer, the process orders one. And we've actually got 3 log streams. Now, what that is telling us is that the Lambda service has um, has instantiated 3 concurrent instances of my consumer function. In other words, it's created 3 micro VMs, loaded each of those micro VMs with my consuming Lambda, my processed orders Lambda. And as we'll see in a moment, each of these log streams will tell us which of the messages, which of the orders were sent to which of the Lambda instances. We have 7 orders in our 6, I think 6 orders that we wrote to the queue, but the Lambda service decided that it would take that, and more than likely when the Lambda service polled SQS for messages from the queue, the SQS service would have returned the 6 orders to the Lambda service. The Lambda service then actually would have split those up into subgroups and sent some of the orders to one of my consumer Lambda instances, others to another one of the instances, and the remaining orders to the third instance. So let's look specifically at what each of these consuming Lambda instances, these are concurrent instances. Let's see what they actually received. And if you look, let's see. So here's user 6. So it looks like this log stream, which is linked with one of my concurrent consumer Lambda instances, it only received one order, which was related to the order for user 6. Okay, if I'm reading that right. So let's look at the second log stream. It received a sub batch related to the user 1's order, user 2's order, and that's it. So we have user order 1, order 2, and order 6 were handled by the 2 Lambda log streams that we looked at so far. So hopefully the remaining log stream, which is this one, should have gotten the rest of them. That being 3, 4, and 5, I guess. And sure enough, 4, 5, and did I misread it? So it's got 4 and 5. So where has order 3 gone, I wonder? Let's go back and check that again. So that's just order 6. This is order 1, 2. And this is order, let's see, order, oh, there's 3 there. Oh yeah, there's 3, 5, and 4. Okay, so we've gotten all 6 orders. So, and if I ran it a second time, it's obviously, it's going to be different every time. If I cleaned out the log groups and triggered my producing Lambda again, then, we might only get 2 log streams, or we might get 4 log streams. It kind of varies from time to time. But either way, I have proven that, what have I proven? I've proven that the Lambda service has created a number of concurrent instances, in this case, 3 concurrent instances of the consumer, and the batch of messages, which was the full 6 orders that it received from SQS, the Lambda service actually decided to split that batch up into, let's call them sub batches, and gave a sub batch to each of the 3 concurrent instances of the consumer that it decided to instantiate. Okay. Let's go back to the slides. So I've talked about that. I've talked about the consumer code. And when I actually ran this earlier, when I was preparing these notes, in that particular execution, it actually created one, two, three, four, five. It actually created 5 concurrent instances of my consumer, which I'm kind of commenting over here. So it does vary as to how many concurrent instances it will create. I guess depending on how busy the Lambda service is. Right. The other thing is, and this is a characteristic of the SQS service that I would have mentioned at the very beginning, and that is that there's no guarantee that the order of the messages that the consumer receives is the same as the order in which the messages were written to the queue. That's just a characteristic of SQS that usually is not of concern, really, but you do need to be aware of it, okay? That there's no, and we kind of saw that, right, when we looked at one of the log streams there. I think it was the third one. It seems to have got order. I'm struggling with these every time I try and read them, but oh yeah, like it's got 4, 5, and I've lost 3 again. Where's 3 gone to? Oh yeah, it's got 4, 5, and 3. It didn't get them in the order of 3, 4, and 5. It's got them in a different order. So there is no guarantee as regards the ordering of the messages that are passed to your consumer. And that's usually not a problem. Well, it's usually not a problem. If it is an issue, if the consumer absolutely has to get the messages in the same order that they were written to the queue, then you can actually configure your SQS queue, the SQS service, I guess. You can configure it such that it will honor the order of the messages. That does have impacts in terms of the performance of SQS, because it now has to do some extra work to make sure that the messages are in the right order. That would be called a FIFO queue, first in, first out. So there are 2 types of queues, really, 2 types of SQS queues. Let's call them an ordinary queue, which is what we're looking at. But there's also something called a FIFO queue, which we won't look at. Okay. If we just change things a little bit, supposing, the fact that the Lambda service there created 3 concurrent instances, perhaps that's a little bit excessive. Maybe we only want the Lambda service to never create more than 2 concurrent instances. Can I control that? And the answer is yes. So if I go back to my CDK code, there is a property it's not a property of the queue now, it's a property of the event source, which is here. So if I now enable this line here, this is now saying don't create more than 2 concurrent Lambda instances. So if I save that and I redeploy, and I get an error. Why is it giving me an error? I don't think I made any changes to my code. No. That's actually good there now that you saw there that it threw an error. And I just ran the command again, and this time it's running successfully. And that can happen to you, and it may have happened to you. So if you do get an error when you try and do CDK deploy, obviously check to see, well, maybe it's a meaningful error. You do check that first. But if you can't really rationalize why it's giving you an error, there's no logical, as far as you can work out, reason as to why you're getting an error. It just may simply be a networking issue. And you just run the command again. But the caveat obviously is you do check the error that you're getting, which I did there, and this didn't make any sense because I knew that the only change I had made was the change that you saw me making, and I know that that is not a source of an error. That was the only thing. That's the only line I changed. So that's just a small observation there that actually turned out to be maybe useful. Right, so I've redeployed, and maybe I'll just clean up my CloudWatch logs. And now in this case, when I run it, there will definitely only be 2 log streams for the consumer. And let's just prove that. Sorry, did I delete the log streams? There are other log groups. Oh, okay. Let's trigger the Lambda. The producer Lambda, its name is the same as before. So I can just rerun this command. Again, there's going to be a delay before the consumer Lambda runs. So if I do another refresh, still not. Okay, and this time now there should only be 2 log streams, which there are. And again, just check them, but on this occasion, one consumer got order 1, order 2, and order 4. And so the other one should get 3, 5, and 6. And indeed, it does get 3, 5, and 6. But you saw there in the previous log stream that again the order was not 1, 2, and 3 or whatever it was. It wasn't in order. They happened to be in order in this case. Anyway, it has respected the concurrency setting that we made in our CDK code. So there's only 2 log streams in this case. And if we kept on piling messages, kept on writing messages into our SQS queue, the Lambda service is never going to create more than 2 concurrent instances in this case. of the consumer. That might be an issue in real life because the consumer may not be able to keep up with the volume of messages. And if you as the developer of the application, if you're happy that the lambda is going to fall, the consuming lambda is going to not process the messages as quickly as it would if there were more concurrent instances. If you're happy with that, then that's fine. Leave it as just two. No messages are going to get lost because we said the messages are going to be persisted for a minimum of 4 days. So eventually the consuming lambdas, my two concurrent consuming lambdas, will catch up, so to speak. Okay, back to my slides. So we've demonstrated controlling the number of concurrent lambdas. Now, this is just a general characteristic of SQS queues. So when a message is, when a consumer reads a message from a queue, the message remains in the queue, but what the SQS service does is it makes that message invisible to any other consumers for a period of time. Okay. And this period that it makes the message invisible for is called the visibility timeout. So when a message is read by a consumer, immediately SQS starts the visibility timeout period for that message, which according to this slide here and the documentation, the default is 30 seconds, which means that the consumer has to process that message and ask SQS to delete it within the 30-second period. If the consumer doesn't finish processing the message within the 30-second period, then that message will become visible again, and potentially other consumers may get to read it, which presumably you don't want that to happen. So you might want to actually increase the visibility timeout period to allow for that. And that's just a tuning issue, really. Maybe for some messages, the amount of processing that the consumer has to do is such that you have to increase the visibility timeout period, which is a characteristic of your queue now. This is at the SQS queue level. Okay, so by default, this message visibility period is set to 30 seconds. The consumer has 30 seconds to process and delete the message. Otherwise, the message becomes visible again. And what you set the timeout period, what you set the visibility timeout period to be, as I said, that is a tuning issue. So, you test your application and you either increase or decrease the visibility timeout based on your kind of performance testing that you do. Now, we're not going to go near that, but and I'm just saying here that if you set the visibility timeout period to be too high, then that means that a message which should be, if it's too high, then we're saying the consumer, if it's too high, and let's say the consumer actually, let's say it throws an exception while it's processing the message, then no other consumer has the opportunity to process that message because the visibility period will prevent them, other consumers, from actually being able to read the message. So, i.e., you can't just set it to a very high value. If you set it to too low a value, then that raises the possibility that a consumer will get the message, start processing it, but before it has finished processing it, the visibility period will have expired, and another consumer will be processing the message in parallel. Now, with SQS, we don't really want more than one consumer to process a message. That's an objective of ours. If we want more than one consumer to process a message, then we should not be using SQS at all. We should be using SNS. Okay, that's this visibility. I'm not going to play around with the visibility. You can set it obviously at the CDK level, but I'm not going to play around with it to show you different kind of scenarios. So we're going to move on to something else, which is important to us, and I will be able to demonstrate it to you. And it is this concept of what are called dead letter queues. So I'm saying here that if a consumer does not process a message, a batch of messages, sorry, if a consumer does not process the batch of messages that it receives, if it doesn't consume them within the visibility period. By the way, when I was talking about the visibility period on the previous screen there, it actually applies at the batch level, not at the individual message level. So your consumer polls the queue, it receives a batch of messages. The visibility period is set for that entire batch. So the consumer has to process the entire batch within the visibility period. However, let's supposing it arises that a consumer receives a batch of messages, and let's say it throws an exception, or it is not able to well, let's deal with the throwing exception kind of scenario. Let's say it throws an exception while it's processing the batch of messages, which means that the visibility period is going to expire and our messages are now going to be available again for another consumer or the same consumer to process them again. Now, that may be a good idea, right, to actually give the consumer a second chance at processing the messages, because maybe it threw an exception simply because, you know, it couldn't make contact with some other service that it was trying to communicate with. And so maybe the second time it gets to process that batch, it actually manages to process them successfully. In general, though, when the consumer throws an exception while it's trying to process a batch of messages, then that batch of messages is put back into the SQS queue again. Although really what actually happens is the visibility period is set back to, is kind of reset back to 0, and the messages are all visible again. Now, that will keep on happening though, you know, if on the second and third and fourth and fifth attempt at trying to process the batch of messages, my consumer keeps throwing exception, the messages will just keep being put back into the queue. And clearly that's not a good idea. So what we can do is we can configure our queue such that after a certain number of attempts by the consumer to process the messages, those messages will now automatically be removed from the queue and they will be put into another queue called the dead letter queue. And that's what I'm trying to illustrate in this simple image over here. So here's our normal queue, if you like, and here's our consumer. And it looks like our consumer is receiving the same batch a number of times because it cannot process them either within the timeout period, its own timeout period, or because it's throwing an exception. Either way, the messages are being put back into the queue and it gets them a second time. So there's a number of these retry attempts happening, but eventually we want those messages to be written into another queue, which we refer to as the dead letter queue. And what you do with them in that other queue is completely up to the nature of the application. Typically, you would have a consumer, because this dead letter queue, it's an ordinary SQS queue. It just happens to have the role of a dead letter queue for this queue. But you'd have a consumer here which processes this queue. And whatever that means, it depends on the nature of the messages. So this dead letter queue idea is a place to put messages that the consumer was not able to process for whatever reason. We can't just ignore, we can't just drop those messages completely and forget about them because, if they were orders, if they were customer orders, then we need to get back to the customer or whatever. So we can't just delete them from this queue and forget about them. So this dead letter queue serves this role of dealing with uh, messages that could not be processed in your regular queue. So number one here, I'm saying we can set a threshold of how many times my consumer tries to process a batch of messages from the normal queue. That threshold is what's referred to as the maximum receive count, kind of an odd name. Okay. And if the maximum receive count is reached, then the role of the dead letter queue kicks in. It's useful. So yeah, it's mainly used for kind of debugging your application, your application in production now, though, not at development time. What am I saying here? Separate consumers. That's okay. So what I've done is I'm sticking with the same scenario. Here's my producer Lambda generating orders, putting them into this queue here. But if there's a bad order, so the messages are passed on to my process orders Lambda, and this Lambda is going to throw an exception if an order object is missing any attributes or is not structured properly. It's going to throw an exception. And what I want to happen is when it throws an exception, the particular batch that bad order is part of, that batch is put into this queue here, which is my dead letter queue for my orders queue. And I've got another Lambda over here, which is polling this queue for messages. Now, this Lambda isn't doing anything interesting. It's just console logging them. But in real life, it would do something useful. Okay, so let's reconfigure this application now to reflect that architecture. So in my CDK code, I've now got a second queue, but you can see from the declaration, you can't tell from the declaration that this queue is actually going to play the role of a dead letter queue. It's an ordinary SQS queue. However, in my orders queue, I'm adding some extra configuration, linking up the two. Okay, so this dead letter queue property of my orders queue, and I'm telling it, well, here's the queue that is going to play the dead letter queue, which is the one just up here. This property here, what that is saying is it's only giving the consumer of this queue one opportunity to process a batch of messages. If it fails on the first attempt, then if it fails on the first attempt, then that batch of messages should be written to my dead letter queue. Okay, so I'm only going to give it one opportunity. Here, this is the same as before. I've got a new Lambda though. This Lambda here is going to be the Lambda that processes the messages in the dead letter queue. And I need to, this is just making the dead letter queue the event source for that new Lambda that I've just enabled. And okay, it's going to poll it. Again, I've set it to 5 seconds. And I've set the maximum concurrency to 2. That's all right. Now, if I go to the producer, in this case, I'm going to, what am I going to do? I am going to enable this order here, which is a bad order, and it's from user X. Okay, so it's missing this property here. And that's why I introduced these extra types. Where have I got them? I've declared a new type here called, let's see, a bad order. And a bad order, I'm just using the partial utility type from TypeScript, if you remember. Partial utility type makes every property of this optional. Order was declared in the shared file, which was here. So here I'm saying all of these 3 properties are mandatory, whereas in the bad order type, I'm saying they're optional. And then I'm saying I'm declaring a type called order mix, which could be an order or a bad order. And that's why this array here is an array of type order mix, because now I have one order, this one here, which is a bad order. Okay, and I'm going to also just add on some more orders to my list. Though I don't have a really good reason for doing that, but let's just do it anyway. Okay, so that's the generate order. So I haven't done anything new really, other than just added in some extra orders to my array and added one bad order. The process orders consumer, it's now here, it's checking to see if an order is properly structured. And so the bad order in my array will cause this to be true, in the sense that there is an order which is incorrectly formatted. I am console logging that for the purpose of CloudWatch, but here's the important thing. I'm throwing an exception. And so when this exception is thrown by my process orders consumer, that will cause the batch of messages that it is processing to be sent to the dead letter queue. And here's the function that processes the dead letter queue, and it's not doing anything interesting other than console logging the message, each message in the batch. Okay, so let's redeploy. So we can just go back to this guy. It now looks like I have, just based on the numbering, I have I've got 9 valid orders and 1 invalid order. Okay, and I still have, in terms of the concurrency limits, I have set the concurrency for the process orders consumer to 2, and set it the same for this one. Okay, so it's still deploying. I'll go back to CloudWatch logs. I'll just do a quick cleanup here. Still deploying. And what I'll do is I'll just trigger my my producer lambda again. It's going to write 10 messages into the queue, 9 good orders, 1 bad order. The Lambda service is going to poll that queue. It'll get the 10 messages. It'll split them up in some way. We can't really predict how it's going to split them up into 2 subgroups. And there are only going to be 2 subgroups because I have set the concurrency. I've set the concurrency limit for my process orders to 2. So it's going to split them up into 2 subgroups. One of the subgroups or sub batches, if you like, will contain the bad order. And whichever Lambda gets that, it's going to throw the exception. That sub batch is going to finish up in the dead letter queue. And we'll see that the Lambda that deals with the messages in the dead letter queue, we'll see that it outputs all of the messages that were in that sub batch. Okay, so it's the same producer Lambda now, so its name is going to be the same as before. And so let's go. Okay, the consumer of the orders queue hasn't run yet or yet. Okay, so the consumer has run now at this stage, but we have a second consumer. The second consumer is for the other queue, but that's going to be delayed until there are messages in the dead letter queue. So if I refresh again, no, still hasn't ran yet. Give it one more go. No. Okay, let's just look at this one anyway. Yeah, this one here. There should only be 2 log streams, which there are, and we've no way of knowing which log stream has the bad order in it. So we're looking at user 1. Here it goes. Is that the one? Let's refresh that. Okay, so it looks like this log stream only received user 1, and it looks like the bad order one, because that's why I'm getting the exception here. Although, oh yeah, there's user X there. That that came from the console log in the consumer. Let's just go back and look at that consumer again. This console log here. It's console logging the actual detail of the bad orders. Okay, before it throws the exception. Now, just before we leave this log streams, or this log group, if we look at the second log group, it got the majority of the orders. So, though some of them were missing, I think. So it's got user 1. I'm misreading that. User 3, 2. Where are all the other orders gone to? Let me do a refresh here again. Doesn't seem to be adding up. Okay. See now again. So we're getting user 1, and then we're getting the error. So we're getting user 1, user X, and then the error. I'm wondering where all the other orders are gone to them. User 3, user 2. Sorry, user 3, user 7, user 2. Where the other is gone to. Just go back to log groups. So I have my 3 log groups at this stage. This is for the new one is for the lambda that processes the dead letter queue, which is this one. Just look at that for now anyway. It only has it has 2 log streams. Oh, okay. I think I know what's after happening. Okay, let's go back. Sorry. Let's go back. I should really have copied that. Okay, let's go back to this one here. Sorry, this one here. So, and let's look at this log stream. So this is a log stream that processed order order 1, order 7, and order 2. Okay. 1, 7, and 2. Okay. And so the other one, this log stream got all of the other orders, including the bad one. But how come we're not seeing all of the other orders here? And the reason, of course, is that once it hit the invalid order, which was the user X order, this one here, once it hit that, it threw the exception. And it didn't get to process the other orders that were in this batch, which would have been, oh God, I'm not keeping track of the count now, but there were other orders in this batch. We had, what was it in total? We had 10 orders. So I think there would have been, there was only 3 orders in the other batch, from recollection. So this Lambda instance would have gotten 7 orders. It managed to process one of them for user 1, but then it hit the bad order and it threw the exception. So all of those 7, I'm saying it's 7 for now in my head anyway, all of those 7 orders would have been written to the dead letter queue. So, and you know, there are actually good orders that are appearing in the dead letter queue. And I knew that was going to happen. If we now look at the log group for this lambda, the one that processes the dead letter queue, it would have received 7 messages, and the lambda service split those 7 messages, that batch of 7, into 2 sub batches and divided them up between 2 concurrent instances of this lambda function. And there are only 2 because in my CDK code, I said that, I look at the CDK code, I limited the number of concurrent instances of the lambda that's processing the dead letter queue. I've limited that to two concurrent instances as well, which is why I've got two concurrent two log streams here. And again, if we just arbitrarily look at them, this log stream got order 4, 6, 5, and X. So it did actually get the bad one. So it's gotten 4 messages from the dead letter Q, which according to my calculation, which is probably wrong, is it 4, 1, 2, 3, 4, 5 actually, sorry. 1, 2, 3, 4, 5. Am I wrong a second time? 1, 2, 3, 4, 5, 6. Okay, let's look at the other log stream. And it just got 1, and 6 and 1 is 7. So thankfully I was right. There's a total of 7 messages that were written to the dead letter Q. Okay, now again, if I cleaned out everything, all my log streams, and ran it again, I'd get a different scenario. Are we on time? I'd get a very different scenario. Just do a quick attempt at that. Delete all my log streams. Let's trigger it again. And clearly this is something you should play with. Well, I haven't given you the code now that I think about it, but you'll get an opportunity to configure a dead letter queue in the lab, although it's kind of at the back end of the lab, I think. Let's just see what happens in this scenario anyway. Let's look at the process. This one here. I know for certain there's only going to be 2 log streams, but how it split up the messages is completely arbitrary. In this case, we got user X straight away over there. Okay. So whatever other messages, whatever other orders were in this batch have now been sent to the dead letter queue. And let's see, if we look at the other log stream, we'll get an idea as to how many were written to the dead letter queue. So this is the second log stream. So we've got user 4, user 5, user 6, user 7, user 3, user 8. Okay, quite a lot actually. So it's 1, 2, 3, 4, 5, 6, if I'm right. 1, 2, 3, 4, 5, 6, 7 actually, sorry. Got user 9 down here. 7. So that means in the batch that were written to the dead letter queue, there were only 3 messages. And if we try and confirm that, just do a refresh here. Here's the failed. It's only 1 log stream here, which kind of makes sense. It didn't need a second one. And this log stream should show, hopefully, 3. So user 2. Is it catching me out yet again? User 3 and user 1, sorry, user X, sorry, user 1, user X, and 2. That doesn't add up. It should be 3, I thought. Okay, there's only 2. I'm not going to spend too much time now. It just means I've added things up incorrectly, which wouldn't be. I'm just going to do one more checking it and then I'll leave it. Just getting a little bit monotonous. Which one had all of them? No. Count these again. So it's 1, 2, 3, 4, 5, 6, 7. It is 7. There should be really 3 in the other group, but I'm sure I've just miscalculated it slightly. Hopefully you get the general gist of it. Now, the fact that there are in my dead letter queue, because of the way SQS works, in my dead letter queue, there are valid orders appearing in it. And really, the Lambda that processes the messages in my dead letter queue, it should really put the good orders back into the orders queue again. Yeah, it should write them back into it because they're good orders. They shouldn't be ignored. So that would be something that would occur or should be handled, in a production application environment. Okay, so it's quite tricky, but there you go. Now, that's the notion of a dead letter queue, and I've talked through the code, so I can skip over those slides. Okay, I can skip over all of that. And here I'm just kind of explaining what happens kind of in one particular scenario, which I've tried to illustrate there. You may need to rewatch the video to clarify your understanding of how DLQs actually work. And this is just a screenshot from one particular execution of this mini application. So I'm not going to talk over that slide. Okay, so that's this SQS service. We've looked at parts of it. There are lots of other aspects to it, though, which we won't get to look at, but that's okay. If I can just go back to this slide way back here. And what I'm trying to get across on this slide, if I even go back further, let's see, yeah, I'm saying here that SQS is a fully managed, which means it's serverless really, even though it predates serverless. I'm saying it's a distributed queuing service. Now, I'm trying to explain this distributed characteristic of SQS. I'm trying to explain it in this slide here. And so it turns out, right, that when you create a queue, what the SQS service does is it creates kind of multiple copies of the queue on various nodes in its network. Now, each copy doesn't have all of the messages in the queue, it just has some of them. So in the image that we're looking at here, it looks like we've got a queue and it has been split over, 1, 2, 3, 4, 5, 6, 7 different nodes. 2, 4, 6. I'm bad at counting today. 7 different nodes on the AWS network. Now, and the reason it distributes them over a number of nodes has got to do with the availability characteristic. If it stored a queue just on one node, which is one computer, and that particular node or computer happened to be inaccessible due to networking issues, then when a consumer wants to read a message, it's just going to get back an error saying that the queue is not accessible. That's clearly not a good quality of service. So that's why it distributes your actual queues across multiple nodes. That's number one. Number two then is when a consumer, now I'm showing three consumers here, but we're just we're just only interested in the case where there's one consumer. When the consumer asks and in our case, the consumer, let's say, is the Lambda service. When it asks the SQS service for a batch of messages from our particular queue, what the SQS service does is it based on an algorithm, it selects a subset of the nodes. And for this particular scenario, let's say that the nodes that it has selected are the ones that are in gray. So it has selected this one and this one and this one. And it has asked those nodes to return a batch of messages from the queue. Now, the messages are numbered A, B, C, D, E. So, and because each node is not going to have every message in the queue, it's only going to have some of them. And if you just kind of looked at the ones that were selected, this one here and this one and this one, then the messages that are returned are messages A, B, C, and D. If you just follow the kind of numbering. So even though there's a message E, is there an F in there? I don't think there is. Even though there is a message E, because the message E wasn't in either of the nodes that were selected, then E is not going to be included in the response. But maybe when the consumer polls at a later stage, then this node here or this node here will be selected, and at that stage, message E will be returned to the consumer. So that's how it actually kind of works behind the scenes. It distributes your physical queue in terms of storage. It distributes it across multiple nodes. Each node gets some of the messages. It doesn't get all of them. And again, we're not interested in the producer of the messages here, but when a producer writes messages to our queue, then the SQS service will make copies of that messages across a subset of these nodes. So that kind of explains this distributed nature of SQS queues. Also, so if you just take these two here, right? So this node has message C, B, and D. This one also has B and D, but B and D will not be included twice in the batch of messages that are returned to the consumer. SQS will guarantee that because each message actually will have a unique ID. And so as the SQS service is creating the batch here, I mean, first of all, each of these nodes is going to respond back with messages to the SQS service. And the SQS service then is going to filter out any repeating messages. So that's why there's only one copy of each message sent back to the consumer. We're kind of guaranteed of that. Okay. Hopefully, now I just got this image from the SQS documentation. So if you're a little unclear on what I'm trying to get across there, just Google SQS SQS message storage, I guess. I'm not sure what Google search I did to come across this, but it's not really, you don't really have to understand how SQS works at a deep level, but I think it's kind of interesting to know that that's what's actually happening behind the scenes. And the multiple copies The whole point of multiple nodes storing a subset of the messages in a queue is to ensure the availability of your queue to your consumer at all times. Right. That's the SQS service. The next service I want to look at, which is also a messaging service, is the SNS service. Similar, but different. So SNS, which stands for Simple Notification Service. Again, it's a serverless. In this case, I'm calling it a serverless publisher subscriber, or PubSub for short. You may have heard the acronym PubSub in other modules that you've studied. So it's a PubSub or publisher subscriber messaging service. And what's the difference between SQS and SNS? Well, the difference is that with SQS, only one consumer will ever get to read a particular message. Whereas with SNS, you can have multiple consumers and each consumer will get every message in the queue. Although we don't call them queues in the case of SNS, we call them topics, but essentially they're the same kind of idea. So publishers write messages to a topic. Subscribers, which is the equivalent of our consumers, we just use a different language. In SQS, we talked about producers and consumers. In SNS, we talk about publishers and subscribers. Publishers write messages to an SNS topic. Subscribers receive those messages. But every subscriber will get every message that was published to a topic. So yeah, so what if you want to send a message to many consumers? That's when SQS won't do it for you. That's where SQS is often referred to as a point-to-point messaging service. You know, you've got one producer, typically anyway, one producer that wants to send data to one consumer in an asynchronous manner. That's where SQS comes in. SNS is where you want a producer to send a message, to send data or information to many consumers. And each of the consumers will process the message. Each of them will process it in kind of parallel. So the event producer, publisher sends messages to one SNS topic. That's okay. Many event receivers, i.e. our subscribers, can listen. We talk about listening to a topic for messages. The other difference between, well, sorry, I'll come to that later on. Actually, it's not actually. And you can see here in the top right, you know, SNS is a very old service as well, relatively speaking, in the lifetime of the AWS platform. It's back in 2011, which again significantly predates the whole serverless architecture style, although SNS and SQS are used extensively on or in serverless applications. Subscribers. Now, you know, even in the case of SQS, right, our producer in the case of SQS was a Lambda, but we could have used other things. The other services can be producers of messages for a queue. And the same is the case in the case of SNS. The publisher, it could be a Lambda, but it actually could be an SQS queue. It could be a HTTP, i.e. an API gateway. Could be it's the subscribers I'm talking about, sorry. The subscribers could be an SQS queue. So a producer, so I'm getting the language wrong, a publisher writes a message to an SNS topic. the subscriber, one of the subscribers could actually be an SQS queue, and we will see that an example of that. Or the subscriber could be an API gateway, or it could be an SNS messaging subscriber. Could be a Lambda, of course. I don't think I mentioned, or I do mention Lambda here. I mentioned Lambda here as a subscriber. You could have an email subscriber, which we won't see, as in when a message is published on an SNS topic, then that triggers a service called the SES service, the simple email service. And what the SES service does is it sends off emails to a particular destination. So you could trigger the sending of an email as a result of a message being published on a topic. Or you could send an SMS message as well. We'll only see examples of SQS being a subscriber and Lambda being a subscriber. On the other side, on the publishing side, Lambda could be a publisher. S3 could be a publisher. Other services as well could be the publisher. So it's extremely flexible, as indeed is SQS, even though we didn't see anything other than Lambdas being used. Features integrates with lots of services from the publisher side. Oh yeah, I've just been mentioning from the publisher side, Lambda could be a publisher, S3 could be a publisher, CloudWatch could actually be a publisher, as in when a CloudWatch alarm, if you're familiar with CloudWatch alarms from earlier modules, when a CloudWatch alarm is triggered, that could cause a message being written to an SNS topic. And there are other possible publishers as well. There's lots of encryption going on in the SNS service, but it's kind of similar to SQS. There's in-flight encryption. That is when you're either reading or writing to an SNS topic, you're communicating over a network, but that communication is automatically encrypted by the SNS service. Also, as your messages are resting in the SNS topic, they are encrypted. So there's at-rest encryption. You can have message filtering, which is something that we'll look at in a couple of lectures' time. The idea there is that, okay, a subscriber has the potential to read all of the messages in an SNS topic, but maybe it's only interested in certain messages, and you can express the messages, the types of messages that it is interested in through this filtering configuration. And we'll see that later on, as I said. Security is kind of similar to SQS, really. You've got access control security. So, you know, for a publisher to be able to send messages to an SNS topic, it has to have the necessary IAM permissions to do that. There's also what are called SNS access policies. That is useful if you want to allow a publisher from a different AWS account to access an SNS topic in your account, you know, cross account access, in other words. Or if you or when you have a publisher that is something other than Lambda, when you want to give it permissions to write messages to an SNS topic, for example, the S3 service, which we'll see in the lab actually, to allow the S3 service to publish messages to a topic, it needs to have the necessary permissions, and we do that through what are called SNS access policies. Scaling is built in automatically, so there really is no limit to the throughput of messages for an SNS topic. We have the DLQ kind of idea as well. Although it works slightly differently to SQS. Sorry, an SQS queue for messages that can't be delivered to the subscribers. Okay, so it looks like the DLQs now are their role is slightly different. If for whatever reason the SNS service cannot reach a particular subscriber in order to pass a message to that subscriber, then it will put that message into a dead letter queue, an SQS queue, and then you can have a whatever, presumably a Lambda that is processing those particular messages. So it's kind of for the exceptional scenario. So we talk about topics in relation to SNS. So an SNS topic, I'm saying, is a logical access point that acts as a communication channel between your publisher and your subscriber. A topic lets you group, okay, multiple endpoints. Oh yeah. So in the image here, okay, I've got my publisher, which is writing messages to an SNS topic, and I've kind of already indicated this, the subscribers, can be varied. You can have Lambda subscribers, SQS subscribers, HTTP here really kind of means an API gateway could be a subscriber. The email service, the SMS service. So these are all subscribers that receive all of the messages that are sent written to a particular topic. And they kind of run in parallel, I guess. Do we have time for an example? Probably not. It's probably not a good idea now for me to dive into this. So I think I'm going to hold there. And again, to go back to my lab, which is accompanying this. And I spoke about this at the beginning, really. You will only be able to get, so this is the first page in the lab. You will be submitting this lab as well, although, it's going to span over a number of weeks, so there isn't really any pressure in getting this lab completed. But you will be able to do this section. And in this section, what we have is, the idea is that we will be able to upload an image to an S3 bucket. And the S3 service is going to write a message to an SQS queue. And the message will contain the details of the object that has been written to the bucket, or that has been uploaded to the bucket. And we are going to have a Lambda function, which is a consumer of messages to this queue. And once it receives a batch of messages, in the message will be the full details of the particular bucket and the object. And so it has the capacity, provided we give it the permissions, it now has the ability to essentially download the object locally and process it. Yeah. That's what you will be setting up in this page here. And then we take it on further, where we bring in, what are we doing here? We're bringing in SNS, so you won't be able to do this section. But we now have, when images are now uploaded to our bucket, that will cause a message to be written to an SNS topic. We have 2 subscribers to that topic. One subscriber, well, they're both Lambdas actually, as it turns out. Is that right? They're both Lambdas. Sorry, no, they're both SQSQs subscribers, and those SQSQs have Lambda consumers. So the architecture is getting quite involved there. But because we haven't looked at examples of SNS, you won't be able to complete that section. Okay, I am going to stop there. And as usual, I don't give you a chance to ask questions, which is probably not great, but there's always the labs as an opportunity to ask questions. So I will leave it at that for today, unless there are any questions more generally from anybody. No. Okay. So I will talk to you on Friday at the labs. Thanks.